This is the HSS Interactive Network. Welcome to this edition of Improvement in Action. I'm your host, Phil Nielsen. HSS uses a systematic approach to improving processes. The Demotic model helps us improve quickly and with a high level of confidence. This podcast focuses on the analysis step of the Demotic improvement model. Before we dig too deeply, it will be helpful to see the Demotic model in its expanded version. The Demotic improvement model starts with define, advances to measure, moves to analyze, travels to improve, and ends at control. The gap between analyze and improve allows us to confirm we have a well-tested improvement plan before we start making changes in the real world. The test or pilot stage fills this gap. The results of the test or pilot program are compared with the desired results of the improvement effort. If the results are not the best we think we can get, we loop back to define and try again. When the test results meet our expectations, then we move to improve and actually change the process. Now let's explore what is meant by analyze. Before analyzing data, the team identifies many possible improvement options. Identifying options is often accomplished through brainstorming, creative thinking, or other similar idea-generating techniques. Once all of the ideas are captured, the data is analyzed to see if an idea has validity. Past and current performance data should be included in the analysis. Most often, the data is identified and collected during the previous Demotic step, the measure step. The first data review should include confirming the data is accurate, reliable, and that sample data represents the whole. After we are confident in the quality of the data, we can apply a number of analytical tools to identify how dispersed the data is, which factors act together and which are independent of others, and what are the vital few pieces of data that tell the biggest story. There are several common tools to analyze these factors, including tables of values, graphs, histograms, Pareto charts, and run charts. The first thing to consider in the analysis step is, are there other options to the way we do things now? As a simple example, pretend with me that I want to cut the time it takes me to drive to work and return home. That is, I want to shorten my round-trip drive time. How might I do that? I could change the times I travel, maybe leave earlier or later to avoid rush hour. I could change the route I drive. Maybe there are fewer traffic lights or school zones on the alternate route. I could choose to speed a little. Maybe I won't get caught. Remember, we want to consider as many possibilities as practical, so I could consider taking public transportation. Maybe it is faster than driving. No matter what options I identify, I'm stuck with a problem. How will I know if I cut my travel time if I haven't measured how long it takes to travel now? So I did measure my round-trip travel time. I measured it every working day in February. There were 20 workdays in the month. Now that I have some data, how can I show it to you? The easiest method is a chart. Here is the day of the week and the number of minutes I spent on my round trip for that day. I used a spreadsheet to store the values and present them to you in chart format. But the chart doesn't tell much of a story. Which of the options for cutting my travel time might work the best? I don't necessarily need more data yet, but I need to know more about the data I collected. Earlier, I said data must be accurate, reliable, and that sample data must represent the whole. This data is accurate within 60 seconds. My dashboard clock does not display seconds, so I captured whole minutes. I did all of the measurements, so I'm sure it is reliable. Finally, the data is a sample. I did not measure an entire year, so summer driving could be different from winter. However, this is all the data I'm willing to collect, and February had some good and some bad driving days. One method of analyzing data is to determine how dispersed the data is. In other words, do we have a great deal of variation between drive times, or are they all close to the same? The original chart does not make that question easy to answer. Here's another way of showing the same values. By compacting the chart, you can more easily see the difference or disbursement between drive times. Can you find the longest time? That's right, 58 minutes on the fourth Monday of February. But even this chart requires you to scan the values and remember what you've already seen. There is an even better way to chart the data that helps show the dispersal. This chart is sorted from the shortest to the longest drive times. Now it is easy to find the shortest, 40 minutes, and the longest drive times. But notice something else. Now you can easily see how many round trips took the same amount of time. Although this data has some wide variations or dispersals, some of the data is identical, which means there is no dispersal. Maybe there's another way of looking at the data that will help. Does any of the data relate to each other? In other words, is there a cause and effect relationship that might be in operation? The compact chart of data does reveal some relationships between drive times. Did you notice Monday most often took the longest and Friday the shortest? Did you also see that Tuesday, Wednesday, and Thursday were somewhere in between? The data I collected doesn't necessarily reveal the actual cause for these differences or similarities. This is a weakness in my Demotic measure step. As you can see, it takes some practice to think ahead during the measure step and collect the right data for the analysis step. Although the data I collected may be incomplete, there are a few more facts that can be revealed in what I did gather. These discoveries have to do with the goal of finding the vital few. What does the vital few mean? Often there will be lots of data, but only part of it helps identify a solution. In the drive time example, I have 20 days of data, but is each day's measurement equally valuable? There are several tools to help find the vital few pieces of data. The first tool is to identify the average. Technically, there are 3 averages which can be calculated. You are probably most familiar with calculating the mean average. That is, add all the values together and divide by the number of values. The mean average treats every value as equally important. The mean average of my drive time is 46 minutes and 42 seconds. But we are looking for the vital few, so another calculation is needed. The mode average identifies the values that occur most often. The mode average ignores values that occur only a few times and focuses on the values that occur most often. In my data, there are 6 modes: 41, 44, 45, 46, 47, and 48 minutes. Another way of thinking about the mode average is to ask which drive time is most likely to happen again. In my case, it is 48 minutes. Of the 20 drives, 4 took 48 minutes. The next most likely drive time is 47 minutes. I did that 3 times. The next most likely drive times are 46, 45, and 44 minutes. They happen twice each. Now, can you see that 5 of the 6 mode averages are 44, 45, 46, 47, and 48 minutes. Altogether, these modes represent 13 of the 20 trips. In other words, it is very likely my drive tomorrow will last between 44 and 48 minutes. The vital few can be identified through 2 simple graphs. First is the histograph. By creating groups with ranges of data and plotting them, you can identify certain drive times occur more often than others can. The second graph is a variation of the histograph. It is called a Pareto chart. This is the histograph sorted into descending order. The category with the largest number of drive times is on the left, and the category with the fewest drive times is on the right. The red line shows the percentage of data as you read left to right. In my drive times data, 45% of the times were between 46 and 48 minutes. 65% of the drive times were between 43 and 48 minutes, and so on. Again, we are trying to find the vital few that have the greatest impact on our problems. There is one final graph that can tell us something about drive times that is not obvious in the charts or graphs we have seen so far. The final analysis tool we will look at is a run chart. We started this session by looking at the days and trip times for February in the order I collected them. A run chart depicts these values graphically. The blue line is the actual drive times from the first of the month to the last. The red line is the average mean time, all values added together and divided by 20 days. The green line is the most common average mode, that is 48 minutes. Do you see it? The 2 averages are relatively close to the center of all the data. But what happened to the drive times in the last week of the month? They increased and decreased more widely than the first 3 weeks of February. In other words, they are more dispersed. I do not have data to help identify a cause for this, but wouldn't it be helpful to know the weather conditions, construction activity, or, well, whatever else might have changed the drive times so much? Again, I need more data. The run chart can reveal patterns that are not obvious in any of the other tools we have reviewed. In a nutshell, analysis involves 1. Identifying possible solutions through brainstorming, creative thinking, or other similar idea-generating techniques. 2. Confirming the data is accurate, reliable, and if it is a sample, that the sample represents the whole. 3. Understanding how dispersed the data is. 4. Which factors might have a cause and effect relationship. 5. What are the vital few pieces of data that tell the biggest story? And finally, 6. Is there a pattern in the data when we look at it sequentially or compared to averages like the mean and mode? Before we go, please take a moment and share your experiences with me. If you are an HSS leader, click on the DMATIC-Analyze line in the discussion board on the Performance Improvement landing page to post your comments. Or you can send me an email message at the address on the screen. Well, that's it for this edition of Improvement in Action. Thanks for joining me, and goodbye until next time.